Hello, my name's Tim, amateur radio call sign M0KEP, and I've recently installed an inverted AL antenna between two telegraph poles, and I want to understand what the feeder losses are. What's the effect of the ATU? Should I fit an ATU at the base of the antenna, or is it okay in the shack before the feeder starts? All of these questions and more I'm going to answer in today's video. So I have my inverted L. That happens to be about 65 meters and that 10 meters. Not that it matters for this discussion. I have a 49:1 unun at that point, and I have a 1:1 choke there to stop any RF from going back down at the coax. So here's my coax. Off it goes into the shack, and in there I have an ATU. Here we go. Now I've always used the ATU like this because it's handy with it being in the shack, and this is all automated with my radio. So I've got my radio sat here. I've got communications that goes into this ATU system. RS-232, and that means whatever frequency I select on the radio, it tells the ATU what frequency it's on and therefore what to tune to. So it automatically tunes. I just turn the knob on the radio and the ATU tunes to that band. Anyway, the output of the radio coax goes into the ATU there. Now I've been told many times, and it makes sense in a way, that really the ATU should be outside here, and it's a very popular option for people to use what are called auto ATUs, and you basically transmit a signal into it on a particular frequency and it tunes itself. It automatically switches. So not only is the coax got to go out of there, we've got to have some power as well to this thing. Now what difference does it really make? So with the is it going to make much difference whether the ATU's outside or in the shack? That's what I want to answer. In order to work this out, I'm going to need to know what is the coax loss. So basically the loss going up to the antenna. There's going to be some coax loss whether I've got an ATU at the end or not. So I want to understand the difference. When the ATU is in the shack, the only difference, as far as I can see, is that there's going to be some power reflected back down the coax. Now that power being reflected back is going to cause some loss in the coax. And I think that's going to be the difference between the ATU in the shack or not. So I need to know how big is the reflection. What's the effect on the ATU? What happens when the reflection gets back here into the shack? So I'm going to try and analyse this thing. So in the case of the ATU being outside, it's quite straightforward. The losses are just the loss going up this length of coax, up the feeder. When the reflections are involved, it's going to get more complicated. I'm going to try and simplify it by first of all assuming that the ATU has been tuned to a 1:1 match here to the radio. So if it's a 1:1 match on the radio, 100% of the radio power is going to be coming out. I'll call that RP. So we've got 100% of the radio power going out, goes into the ATU, through the ATU. And I'm also going to assume that the ATU isn't very lossy, so it's not going to dissipate much of the power going into it. And what goes in must come out. So going this way there, we've got 100% of RP, the radio power. That's going to go up the coax, and there's going to be a loss, the feeder loss, and then it's going to get to the input here of that choke. And there's going to be a mismatch at that point. If the antenna isn't perfectly matched to 50 ohms, there's going to be a reflection. We know that's what happens with the antenna. And that reflection is going to go back down the coax here, and it's going to suffer the same coax loss before it gets back to the ATU. Now here's the interesting thing. When it gets to the ATU, none of that reflected power is going to be able to go through the ATU. Now I know that because if any of the power did go through the ATU and back into the radio, we wouldn't have a 1-to-1 SWR. So I know that all the power going there must be being reflected. At this point, at the output of the ATU, we have 100% of the radio power plus the reflected power. So we've got more power here coming out of the ATU than we're actually putting in with the radio. Is that right? Well, I think it is, and we'll try and measure it. So then that reflected energy goes back up the coax all the way along and gets reflected again at the 1-to-1 choke. You get a reflection that goes back, and at some point after the reflections have gone backwards and forwards a few times, the system will reach an equilibrium where the amount of reflection going back down the cable and the losses and the power coming out of the ATU and the losses have kind of reached a stable state, and all we're left with is the power going into the antenna, which is going to be some fraction, actually sort of 1 minus the reflection coefficient of power going that way. So I'm going to try and work out what this is mathematically and see how much difference it really makes compared to the feeder loss in one direction. I'm not going to go into huge amounts of detail in this. I guess most of you aren't going to be interested in the detail in the maths anyway, but there's some great charts that come out of this analysis, and I just want to give a bit of a background into how I've done all of the calculations. The first thing I had to do was go and get some data on the coax that I'm going to be looking at. So we've got an attenuation table there, which and I've done all the analysis at 10 megahertz, and the reason I've used 10 megahertz is because it has a very high SWR at that point on the antenna. The RG58 attenuation is 4.7 dBs in 100 meters, and the Hyperflex 13 1 dB. I've also needed their velocity factors, so RG58 has a 0.66 and a Hyperflex 13 0.86, and that's the fraction of the speed of light at which the signal travels down the cable. Now, things like the characteristic impedance of the transmission line can be defined using some fundamental constants about the cable itself, and these form what are called the telegrapher's equations. I'm not going to go into those today. They're not necessary for my analysis. The propagation constant, for example, rather than being calculated from the fundamental elements on the coax, can actually just be calculated from our dB loss parameter and a phase constant. So this is what I've used from the manufacturer's data on the cable itself. I then come to a section where I compute many of the parameters that I'm going to use. So I've got some variables here. Feeder loss, that's the type of feeder that I want to analyse in the equations below. The velocity factor of that cable, the 50 ohm coax impedance. ZL, that's the load impedance at the antenna, and I've picked those values there from the impedance measurements that I made using the Rig Expert analyzer at 10 megahertz. To make all of the measurements on the antenna system, I've used a Rig Expert AA55 zoom. It's a really useful piece of equipment which operates both standalone and has a great PC software application called AntScope, and it lets you make measurements and store all of the data on the computer for analysis later on. So these are some of the most interesting equations or constants. So we have gamma there, the propagation constant, and that defines how the waveform progresses down the coax. We've got the voltage reflection coefficient there at the antenna input. The SWR, so this is the calculation of the SWR, which is based on the reflection coefficient. We can see there that the SWR is 8.78. That's the same as the value that we measured using the Rig Expert analyzer at 10 megahertz. There we have the power reflection coefficient, so that's the amount of power that gets reflected at the antenna input. As a matter of interest, I looked at the losses down the different types of coax without anything to do with SWR, and these are the numbers we get. So if I plug in 100 meters, 100 meters is a good number That's the number that they specify the power loss over, and it's also a typical reel size of cable. So we can see there RG58. If we put 100 watts in, we would lose 66 watts at the end. So over half, 66% that is. So Hyperflex 13 loss 20 watts, so just over 20%. So we can more easily visualize this. I've done a plot of power loss and feeder length. So we've got loss in percent up the y-axis and the length along the x-axis. You'll see later on that I use a length of 60 meters in one of my calculations, which is the amount of feeder length of RG58 I happen to use. So we can see there it's kind of 40 odd percent loss. In fact, I calculated it up here. It's 40.48, so about 48% loss at 60 meters. Here I've defined some equations 1 to 4, which describe what goes on in a feeder when some power is reflected at the other end. This will take a bit of thinking about, just bear with me. So end power, okay, so end power is the power which is at the end of the feeder just as it's about to go into the antenna. That's saying that the power at the end of the coax is equal to the power going in plus the reflected power at the ATU multiplied by the loss going up the feeder. Equation 2 is defining the reflected power, and that's equal to the power which gets to the end of the coax multiplied by a power reflection coefficient, so that's the amount of power that's reflected at the antenna, again multiplied by the power left after it's travelled down the feeder from the antenna down to the ATU. Equation 3, the load power, so this is the power going into the antenna, is 1 minus the power reflection coefficient times the end power of the cable. So that's saying that what isn't reflected at the antenna goes into the antenna. Equation 4 is saying that the available power fraction, so the fraction of the available power in the antenna, is equal to the load power divided by the power in. So that's the power going into the antenna divided by the power originally going into the ATU. Now, with the magic of Mathematica, I can simultaneously solve these equations, which saves a lot of hard work. And the simultaneous solutions is this power solutions value here. Quickly show you what that is, but that defines rules for what's happening with these different parameters that go into the equations. I've now defined a variable which I've called available tuned fraction, and what that means is it's the a fraction of power available when using the antenna matching unit or antenna tuning unit. The equation for that is here. Not going to go into the details here, but it includes variables for the feeder length and the propagation constant. And with 60 meters of RG58, it's about 0.27. Converting that to dBs, which is about minus 6 dBs down, so 1 S point. So using all that feeder length and an ATU, it's about an S point down from the absolute ideal. By the absolute ideal, I mean if you've got your radio connected with the shortest possible feeder length going straight into the antenna. So here's the available power versus the feeder length chart, which is showing the percentage of power available on the y-axis there against the length of feeder for both Hyperflex 13 and RG58. This is with the SWR of about 8.7, so the SWR on my antenna at 10 megahertz, and there you can see the difference. So now we've got the theory worked out, I wonder what actually happens in practice. So this is the antenna setup that I'm going to test. I have the ATU in the shack, some Hyperflex 13 goes off through the shack wall into a cabinet outside, And then from that cabinet, there's a length of coax which goes up the garden to the antenna system and connects to the one-to-one choke. I'm going to do all the measurements with the RG58 and leave the Hyperflex 13 for another day or another video. To generate the RF, I've used an ICOM IC7300 and I've put that on RTTY mode, and I'm transmitting about 10 watts out through my ATU and up through the antenna system. I've got this cheap power meter, this RS1000. I don't think it's very accurate, but I'm going to use the same power meter in all positions, so we should get a correlated reading. This is the meter attached to the input of the ATU, and I'm measuring 15 watts. The ATU itself disagrees with 15 watts. In fact, it thinks it's 10.2 watts. And you can see there that the input SWR is 1.19 and the antenna SWR is 2.46. I do trust the ATU display more than the meter, just from experience really. I've been using it a while now in the shack, and the numbers it produces seem quite reasonable. I then moved the power meter to the output of the ATU, so the beginning of the feeder, and you can see there that it is actually measuring more power. It looks about 17 watts on the meter. So you've got 15 in and 17 out. By the time it gets up to the end of the feeder, so this is measuring just before the one-to-one balun at the end of the coax, we've got nearly 10 watts reading, just under 10 watts. So we've definitely lost a lot down the feeder. Do these power measurements that we've made agree with the theory though? The predicted SWR at the output of the ATU is 2.42 and the measured value is 2.46, so very close. The SWR has dropped down to 2.4 rather than the 8.7 at the antenna due to this effect shown in the graph here with the feeder length. I'll go into this in another video. I've calculated the power fractions available at the different points in the system, and at the end of the feeder there should be 0.63. The gain at the output of the ATU should be about 1.2, and the available tuned fraction into the antenna is about 0.27. If we now multiply those fractions by the power input, 15 watts, we get the power at the end of the feeder as 9.4 watts, and the output power from the ATU is about 18 watts, 17.97. So allowing for all the measurement uncertainties, I'm really happy that these results show that the maths must be correct. So now I know that I've got an accurate set of equations which are representing the reality of my antenna. I've combined them all in a general form to create this 3D graph here. And this graph is showing the power loss in dBs down the feeder against the SWR and the length of the feeder. I'm going to try and make sense of a few figures on here. So we've got this top left hand corner here, we've got 0 dBs loss, and that's with an SWR of 1 and a feeder length of 0. Well, that makes sense. And with an SWR of 1:1, when we've got a feeder length of 100 meters, we can see the loss there, which is the loss of just the feeder only over that length. And that's also equal to the loss if you had a remote ATU. So if you had an auto ATU by the antenna, that is the loss you'd see because you're only getting the loss in one direction. If I rotate this graph, and we can see what the difference is between the coax. So we can see there the RG58 has got a lot more loss than the Hyperflex 13. In fact, it's down towards the 6 dB mark, even with an SWR of 1:1. Then by the time we get up to an SWR of 10, we've got a lot more losses. So let's have a look. So 10 is down the center. We're looking at, it's very difficult to see actually on this graph. That looks like about minus 10 dBs. So with a 100 meter length of coax, we're getting quite considerable loss. So minus 10 dBs is a tenth of the power. So you can still overcome it, but it is quite a lot of power loss. You can see that Hyperflex 13 is a much better option. So if you're going for a long feeder and you want to tune it with an ATU in the shack, Hyperflex 13 is much better. Even after 100 meters, we're still, and an SWR of 19 that goes up to. It's difficult to see it, but it's 19. We're still looking at 6 dBs of loss. Now 6 dBs is one S point, and it's quite easy to overcome an S point of loss as well if you've got some more power, if you're allowed some more power. So for example, you could go to 400 watts instead of running 100 watts and you'd get the same effect. So in summary, having an ATU in the shack is a perfectly feasible thing to do as long as you understand the losses that are involved. Having an ATU at the base of the antenna does help a lot, especially with only a QRP radio. You'd really be hard pushed to use an ATU in the shack with a QRP radio. But if you've got some extra power to run and you can overcome the losses, no problem at all. One thing to note on the legality of running extra power, if you get more than 400 watts at the end of the feeder without any reflections, I think that's your limit. I don't think you should allow the losses including the ATU in the calculation. So for example, if you've got a 6 dB loss with an ATU, I don't think you should run 1200 watts to get 400 watts into the antenna. I think you should just take account of the power going one way in the feeder. So accounting for the feeder losses in the one direction, absolutely fine. Feeder losses due to the tuner, shaky ground. Perhaps some of you know better and can let me know, but I'd be very nervous about doing that. I found it very interesting doing these calculations, and I've certainly learnt a lot about how to set the station up with the feeders and the ATUs. I've also done some work looking at the impedance at the input of the feeder line, and there's some very interesting findings there, so I'll show you those in another video. If you think I've missed anything out that's important, or you'd like to know more information about any aspect that I've mentioned today, please let me know in the comments, and I'll see what I can do on a future video. Thanks very much for watching, and please like and subscribe if you enjoyed the video.